What if everything we think we know about the universe is just the tip of the iceberg? For centuries, humans have gazed at the stars, searching for answers, yet the cosmos keeps revealing mysteries that defy our understanding. Take dark energy, for example. This invisible force is pulling the universe apart at an accelerating rate, and we still don't fully grasp what it is or why it exists. It's just one of the countless cosmic enigmas that challenge our perception of reality. Today, we're diving into 22 of the most mind-bending mysteries of the distant universe, questions that stretch the limits of human knowledge and leave even the brightest minds scratching their heads. From the bizarre behavior of black holes to the strange whispers of ancient galaxies, this journey will take us to the very edges of what we know and far beyond. So, are you ready to explore the unknown? Let's unravel the secrets of the cosmos together. Galaxies, those swirling islands of stars and gas, hold secrets that defy our expectations. Take a spiral galaxy, for instance. Its outer edges are spinning so fast that, according to the laws of physics, the stars there should be flung into the void of space. But they're not. Something unseen is holding them together, an invisible hand exerting a gravitational pull strong enough to keep everything in place. This is the first cosmic enigma we're exploring: the nature of dark matter. Dark matter is the universe's elusive architect, making up roughly 27% of everything that exists. Yet, despite its overwhelming presence, it doesn't emit, absorb, or reflect light. It's completely invisible to our telescopes, revealing itself only through its gravitational effects. Think of it like the wind. You can't see it, but you can see the way it moves the leaves on a tree. In the same way, dark matter bends the fabric of space, warping the paths of light and shaping the cosmos on a grand scale. But what exactly is it? Scientists have been chasing this question for decades. Theories range from exotic particles that barely interact with normal matter to entire hidden dimensions we can't yet perceive. The challenge is that dark matter doesn't play by the rules we're used to. It doesn't collide with atoms, and it doesn't glow in the dark. Detecting it requires ingenious experiments like deep underground detectors waiting for a rare interaction, or colossal telescopes mapping the distortions in light from distant galaxies. What does this mean for our understanding of the universe? If dark matter is the cosmic glue holding galaxies together, its true nature could rewrite the textbooks of physics. Could it be a clue to new forces or particles we've yet to discover? Or is it something even stranger, something that challenges the very foundations of how we think about reality? And just as we grapple with the mystery of dark matter, another enigma looms: even larger dark energy, a force even more mysterious and powerful, driving the universe apart at an accelerating rate. But that's a story for the next cosmic puzzle. For now, the hunt for dark matter continues, a reminder that the universe is far stranger and far more wondrous than we ever imagined. If dark matter is the invisible hand holding galaxies together, dark energy is the unseen force pushing the entire universe apart, and it's doing so at an ever-increasing speed. This is the second cosmic enigma we're tackling: the mystery of dark energy. Imagine the universe as a balloon being inflated, with galaxies as dots on its surface. As the balloon expands, the dots move away from each other. But here's the twist: instead of the expansion slowing down over time, as scientists once expected, it's speeding up. Something is acting against gravity's pull, driving the universe to stretch faster and faster. That something is dark energy. Dark energy makes up a staggering 68% of the universe's total energy content, dwarfing even dark matter. Yet, despite its dominance, it's one of the most elusive forces in existence. Unlike dark matter, which tugs on galaxies with gravity, dark energy seems to work in the opposite direction, creating a kind of cosmic repulsion. It's as if the universe itself has a built-in mechanism to push everything away from everything else. So, what could dark energy be? One leading theory is the cosmological constant, an idea first proposed by Albert Einstein. He suggested that empty space isn't truly empty, it's filled with a constant energy that drives expansion. But there's a problem. The amount of energy predicted by this theory doesn't quite match what we observe. Another possibility is quintessence, a dynamic field that changes over time, unlike the static cosmological constant. Think of it as a cosmic wind, shifting and evolving as the universe grows. The cosmic microwave background, the faint afterglow of the Big Bang, offers clues about dark energy's influence. This ancient light, imprinted with the universe's earliest moments, shows how dark energy has shaped the cosmos over billions of years. It's like a fossil record preserving the story of the universe's expansion and the role this mysterious force has played. But the bigger question remains, what does dark energy mean for the fate of the universe? If it continues to accelerate expansion, could it one day tear galaxies, stars, and even atoms apart? Or will it eventually fade, allowing gravity to reclaim its dominance? These are questions that keep cosmologists awake at night, and they remind us just how much we still have to learn about the cosmos. As we wrestle with the enigma of dark energy, another cosmic mystery beckons, one that's equally perplexing and far more dramatic. Enter black holes, the universe's most extreme and enigmatic phenomena. But that's a story for the next chapter of our cosmic journey. Picture this, a black hole, a region of space where gravity is so intense that nothing, not even light, can escape its pull. At its edge lies the event horizon, a boundary beyond which the known laws of physics seem to break down. It's a place where time slows to a crawl and the universe itself appears to hold its breath. But here's where things get truly mind-bending. If something crosses that boundary, what happens to the information it carries? This is the third cosmic enigma we're exploring, the paradox of black hole information. The problem begins with a simple question. When matter falls into a black hole, is the information about that matter destroyed forever? According to the rules of quantum mechanics, information can never truly be lost. It might be scrambled or hidden, but it should always be recoverable in some form. Yet, black holes seem to defy this principle. Once something crosses the event horizon, it's gone, or so it appears. This contradiction is what physicists call the black hole information paradox, and it has sparked one of the most heated debates in modern science. Stephen Hawking brought this paradox into the spotlight with his groundbreaking discovery of Hawking radiation. Black holes, he theorized, aren't entirely black. They emit tiny amounts of radiation over time, slowly losing energy and shrinking. But here's the catch. Hawking radiation doesn't seem to carry any information about what fell into the black hole. If the black hole eventually evaporates, where does that information go? It's like shredding a book and trying to reconstruct the story from the ashes. It feels impossible. Physicists have proposed several theories to resolve this paradox. One idea is the holographic principle, which suggests that all the information about what falls into a black hole is encoded on its event horizon like a cosmic hard drive. Another theory involves firewalls, hypothetical walls of energy at the event horizon that destroy anything falling in, preserving the information in the process. And then there's the concept of wormholes, hidden tunnels that might carry information to other parts of the universe. Each of these ideas pushes the boundaries of our understanding, challenging the very foundations of quantum mechanics and general relativity. But why does this matter? If information truly is lost in black holes, it could mean our current laws of physics are incomplete. It's a problem that strikes at the heart of how we understand reality. Could black holes be the key to unlocking a deeper theory that unites quantum mechanics and gravity? or do they represent a fundamental limit to what we can ever know about the universe? As we wrestle with this paradox, another mystery emerges, one that's equally profound and even more puzzling. How did supermassive black holes, the colossal giants at the center of galaxies, come to exist in the first place? These behemoths, weighing millions or even billions of times the mass of our Sun, seem to have formed impossibly quickly in the early universe. What cosmic forces could have created them, and what secrets do they hold about the origins of the cosmos? The answers might just change everything we thought we knew. At the heart of nearly every galaxy, including our own Milky Way, lies a supermassive black hole, a gravitational titan so immense it defies imagination. These cosmic giants, some weighing in at billions of times the mass of our Sun, anchor their galaxies like silent puppeteers, shaping the stars and gas around them. But here's the real puzzle. How did these colossal black holes form in the first place? This is the fourth enigma we're unraveling, the origins of supermassive black holes. The story begins with a startling observation. In the early universe, just a few 100 million years after the Big Bang, supermassive black holes were already thriving. How could they have grown so massive so quickly? One leading theory is the idea of direct collapse. Imagine a massive cloud of gas collapsing under its own gravity so rapidly that it bypasses the formation of stars entirely, condensing directly into a black hole. This process could have created black holes thousands of times the mass of the Sun in a cosmic blink of an eye, providing the seeds for the giants we see today. Another possibility is that smaller black holes formed from the deaths of massive stars merged over time, building up mass like a snowball rolling downhill. But even this process has its challenges. Mergers take time, and the early universe didn't seem to have enough of it. Some scientists suggest that extreme conditions, like densely packed star clusters or the chaotic environments of young galaxies, might have accelerated these mergers, allowing supermassive black holes to grow faster than we once thought possible. Take Sagittarius A, the supermassive black hole at the center of the Milky Way, for example. While it's relatively quiet now, its influence on our galaxy is undeniable. It shapes the orbits of stars and gas clouds, and its gravitational pull can even trigger bursts of star formation. But how did it grow to its current size, roughly 4 million times the mass of the Sun? The answer might lie in its past, a history of mergers and feasts on gas and stars that were only beginning to piece together. These black holes aren't just cosmic curiosities, they're essential players in the story of galaxy evolution. They can power quasars, the brightest objects in the universe, and regulate the growth of galaxies by heating up or expelling gas that might otherwise form stars. Without them, the universe as we know it might look entirely different. As we ponder the origins of these gravitational giants, another mystery emerges, one that's equally baffling and far more fleeting. Fast radio bursts, or FRB, are brief, intense flashes of radio waves from deep space lasting just milliseconds. What could possibly produce such a sudden, powerful signal? The answer might lie in the most extreme environments in the universe, or perhaps something even stranger. But that's a story for the next chapter of our cosmic journey. In the vast silence of space, a sudden flash of energy erupts lasting just milliseconds, yet releasing as much power as the Sun does over days. These are fast radio bursts, or FRB, one of the most baffling phenomena in the cosmos. They appear without warning, vanishing almost as quickly as they arrive, leaving scientists scrambling to understand their origins. This is the fifth cosmic enigma we're exploring, the mystery of fast radio bursts. First detected in 2007, FRBs are like cosmic fireworks, bursting with energy from galaxies billions of light-years away. Imagine a single pulse of radio waves, so intense it outshines entire galaxies, yet so fleeting it's nearly impossible to catch. To date, we've detected hundreds of these bursts, but only a handful repeat, adding another layer of intrigue to their nature. Take FRB 121102, for example, the first repeating FRB ever discovered. Unlike its one-time counterparts, this burst sends out multiple signals, offering scientists a rare opportunity to study its source. So, what could possibly produce such a sudden, powerful signal? Theories range from the dramatic to the downright speculative. One leading idea points to magnetars, highly magnetic neutron stars that occasionally release colossal bursts of energy. These stellar remnants, born from the explosive deaths of massive stars, could generate the intense radio waves we observe. Another possibility involves collisions between dense objects like neutron stars or black holes, releasing energy in a cosmic crash. And then, of course, there's the tantalizing, if unlikely, idea that FRBs could be signals from advanced extraterrestrial civilizations. While this theory captures the imagination, most scientists lean toward natural explanations, though the truth remains elusive. Recent discoveries have brought us closer to solving the puzzle. In 2020, astronomers detected an FRB originating within our own galaxy for the first time, linking it to a known magnetar. This breakthrough provided strong evidence that at least some FRBs come from these highly magnetic stars. Yet, not all bursts fit this pattern, suggesting multiple sources could be at play. What makes FRBs so fascinating isn't just their mystery, it's what they could reveal about the universe. These bursts travel through vast expanses of space, interacting with the cosmic medium along the way. By studying their signals, scientists can map the distribution of matter between galaxies, uncovering the hidden structure of the cosmos. It's like using a flashlight to illuminate the shadows of the universe, one burst at a time. But the questions don't stop there. Could FRBs be a window into new physics, revealing phenomena we've yet to imagine? Or are they simply the cosmic echoes of extreme events, waiting for us to decode their secrets? As we continue to explore these enigmatic bursts, they remind us that the universe is full of surprises, each one a clue to the grand puzzle of existence. And speaking of cosmic echoes, there's another ancient whisper that holds the key to understanding the universe's earliest moments: the cosmic microwave background, the faint afterglow of the Big Bang. But that's a story for the next chapter of our cosmic journey. Imagine looking at the oldest photograph in existence, a snapshot taken not of a person or a place, but of the universe itself, just 380,000 years after it was born. This is the cosmic microwave background, or CMB, the faint afterglow of the Big Bang. It's often called the universe's baby picture, and for good reason. This ancient light carries secrets about the cosmos's infancy, offering us a glimpse into what the universe looked like before galaxies, stars, or even atoms had formed. But this baby picture isn't just a relic of the past. It's a treasure trove of clues that challenges our understanding of the cosmos and reveals its earliest moments. The story of the CMB begins with the Big Bang, the explosive birth of the universe. In its first moments, the cosmos was a seething, opaque soup of particles and energy. But as it expanded and cooled, electrons and protons combined to form the first atoms, allowing light to travel freely for the first time. This light, now stretched by the expansion of the universe over billions of years, reaches us as microwave radiation, a faint whisper from the dawn of time. The CMB isn't just a uniform glow. It's speckled with tiny fluctuations like the brushstrokes on a cosmic canvas. These variations, though incredibly slight, are the seeds of all structure in the universe. They represent regions where matter was slightly denser or sparser, eventually giving rise to galaxies, stars, and the vast cosmic web we see today. Think of it as the blueprint for the universe encoded in the faintest of signals. But the CMB holds more than just the story of structure. It also reveals the universe's composition, showing that ordinary matter, the stuff we're made of, makes up just 5% of the cosmos. The rest is dark matter and dark energy, the invisible forces shaping the universe on the largest scales. This revelation has been one of the most profound in modern astrophysics, reshaping our understanding of reality itself. Yet the CMB isn't without its mysteries. Take the cold spot, for example, a region of the CMB that's significantly cooler than the surrounding areas. Some theories suggest it could be a cosmic defect, a remnant from the early universe. Others propose it might be evidence of a collision with another universe, a mind-bending idea that pushes the boundaries of our imagination. These anomalies remind us that even the most precise measurements can leave room for wonder and debate. The Planck satellite, launched by the European Space Agency, has been instrumental in mapping the CMB with unprecedented detail. Its observations have confirmed many predictions of the Big Bang theory, while also revealing subtle deviations that keep scientists on their toes. It's like having a high-resolution version of the universe's baby picture, allowing us to see details we could only dream of before. What does the CMB tell us about the universe's origins? It's a reminder that the cosmos is far more complex and mysterious than we once thought. It challenges us to ask deeper questions. Was the Big Bang truly the beginning, or just one chapter in a much larger story? And what triggered the rapid expansion of the universe in its earliest moments? This leads us to the next cosmic enigma, the mystery of cosmic inflation, a period of explosive growth that set the stage for everything we see today. But that's a story that takes us even further back in time, to the very edges of our understanding. In the first fleeting moments after the Big Bang, the universe underwent a transformation so rapid and extreme it challenges our very understanding of time and space. This is the theory of cosmic inflation, the idea that in less than a trillionth of a second, the cosmos expanded faster than the speed of light, stretching from a microscopic speck to something unimaginably vast. It's a concept so wild it almost sounds like science fiction. Yet this theory isn't just a thought experiment, it's a cornerstone of modern cosmology, solving some of the universe's most perplexing puzzles. Take the horizon problem, for instance. When we look at the cosmic microwave background, the temperature is remarkably uniform across the sky. But how can regions that are now billions of light-years apart have reached the same temperature if they were never in contact? Inflation offers an elegant solution. Before the rapid expansion, these regions were close enough to exchange heat, and inflation stretched them apart faster than light could travel. It's like taking a piece of dough, kneading it until it's uniform, and then stretching it out so thin that the uniformity remains, even as the distances grow immense. Then there's the flatness problem. The universe appears remarkably flat on large scales, meaning the density of matter and energy is balanced so precisely that space itself doesn't curve. Without inflation, this fine-tuning would require an almost impossible level of precision in the early universe. But inflation smooths out the cosmos like an iron flattening a wrinkled sheet, naturally explaining why the universe looks the way it does. But how do we test a theory that deals with events so ancient and extreme? One of the most promising avenues is the search for primordial gravitational waves, ripples in space-time created during inflation. These waves would leave a faint imprint on the cosmic microwave background, a signature that could confirm inflation's role in shaping the universe. Experiments like BICEP-2 have aimed to detect this fingerprint, though the results so far have been inconclusive. The challenge lies in distinguishing the signal from other cosmic noise, a task that requires unprecedented precision and innovation. What if inflation isn't just a one-time event? Some theories suggest it could be part of a larger cycle, with our universe just one bubble in a vast cosmic foam of inflating regions. This idea of a multiverse, countless universes, each with its own laws of physics, is both thrilling and daunting. Could inflation be the key to unlocking this grander picture of reality? As we grapple with these questions, another cosmic enigma beckons, one that shines brighter than almost anything else in the universe. Quasars, the luminous hearts of distant galaxies, are like cosmic lighthouses guiding us to the edges of space and time. What powers these brilliant beacons, and what secrets do they hold about the early universe? The answers might just illuminate the story of cosmic inflation itself. Imagine an object so bright it outshines an entire galaxy, a beacon of light so intense it can be seen from the farthest reaches of the cosmos. These are quasars, the universe's most luminous phenomena, and they're powered by something truly extraordinary: supermassive black holes. This is the 8th cosmic enigma we're exploring: the power of quasars. At the heart of every quasar lies a supermassive black hole, feeding on gas, dust, and stars with a voracious appetite. As material spirals into the black hole, it heats up to millions of degrees, releasing torrents of energy in the form of light, radio waves, and X-rays. The result is a quasar, a cosmic powerhouse that can shine thousands of times brighter than the galaxy that hosts it. Take the quasar 3C273, for example. Discovered in 1963, it was the first quasar ever identified, and it remains one of the brightest. Despite being over 2 billion light-years away, it's visible through a small telescope, a testament to its staggering luminosity. But what makes quasars like 3C273 so fascinating isn't just their brightness, it's what they reveal about the universe. Quasars are more than just cosmic flashlights, they're time machines. Because light takes time to travel, we see them as they were billions of years ago, offering a glimpse into the early universe. In their heyday, quasars were far more common, suggesting a time when galaxies were young, chaotic, and brimming with activity. They played a crucial role in shaping the cosmos, heating and ionizing gas, and even influencing the formation of stars and galaxies. But how do these cosmic powerhouses challenge our understanding of black hole physics? For one, they push the limits of energy output. The light from a quasar isn't just coming from the black hole itself. It's generated by the swirling disk of material around it, known as an accretion disk. This disk can be so efficient at converting matter into energy that it defies our expectations, producing more light than seems physically possible. Then there's the mystery of how supermassive black holes grow so quickly in the early universe. Some quasars existed when the cosmos was less than 1 billion years old, yet their black holes already weighed billions of times the mass of the Sun. How did they accumulate so much mass in such a short time? This question has led scientists to rethink the processes of black hole growth, from rapid gas accretion to mergers of smaller black holes. Quasars also reveal the delicate balance between creation and destruction in the universe. While they can trigger star formation by compressing gas clouds, they can also halt it by blasting away material with powerful jets. These jets, composed of charged particles traveling near the speed of light, can stretch for hundreds of thousands of light-years, carving out vast regions of space and influencing the evolution of entire galaxies. As we marvel at the brilliance of quasars, another cosmic mystery beckons, one that's equally explosive and far more fleeting. Gamma-ray bursts, the most energetic events in the universe, last just seconds but release more energy than the Sun will in its entire lifetime. What could possibly produce such a cataclysmic flash, and what can it teach us about the extremes of the cosmos? The answers might lie in the deaths of massive stars or the collisions of neutron stars, events as dramatic as they are mysterious. But that's a story for the next chapter of our cosmic journey. In the blink of an eye, a single event can release more energy than our Sun will emit in its entire 10 billion-year lifetime. These are gamma-ray bursts, or GRB, the most powerful explosions in the universe, lasting anywhere from milliseconds to a few minutes. These bursts are so intense they can briefly outshine entire galaxies. But what could possibly produce such an unfathomable release of energy? This is the ninth cosmic enigma we're exploring, the mystery of gamma-ray bursts. The leading theory points to the deaths of massive stars. When a star many times heavier than our Sun exhausts its fuel, its core collapses under its own gravity, triggering a supernova explosion. In some cases, this collapse forms a black hole, and as material spirals into it, twin jets of energy erupt at nearly the speed of light. These jets, packed with gamma rays, are what we detect as a gamma-ray burst. But not all GRBs come from dying stars. Some are the result of neutron-star mergers, the violent collisions of these ultra-dense stellar remnants. When two neutron stars collide, they release a torrent of gamma rays, gravitational waves, and even heavy elements like gold and platinum. Take GRB 080319b, for example. Detected in 2008, this burst was so bright it could be seen with the naked eye despite originating over 7.5 billion light-years away. For 30 seconds, it outshone every star in the night sky, a testament to the staggering power of these cosmic explosions. But GRBs aren't just awe-inspiring, they are also deadly. If one were to occur too close to Earth, its intense radiation could strip away our ozone layer, exposing the planet to harmful solar radiation and potentially sterilizing life on its surface. Studying these bursts is no easy task. They appear without warning and vanish almost instantly, leaving astronomers racing to capture their fading afterglow. Satellites like NASA's Swift and Fermi missions are designed to detect GRBs in real time, alerting ground-based telescopes to pinpoint their origins. Yet, even with these tools, the fleeting nature of GRBs makes them one of the most challenging phenomena to study. What can these explosive events teach us about the universe? For one, they offer a window into the lives and deaths of massive stars, as well as the violent processes that shape the cosmos. They also provide clues about the distribution of matter in the early universe, as their light travels through vast stretches of space, revealing the cosmic web's hidden structure. And in the case of neutron star mergers, they've given us a new way to study gravity itself, thanks to the gravitational waves they produce. But perhaps the most intriguing question is this: could GRBs be responsible for triggering the formation of life elsewhere in the universe? Some scientists speculate that these bursts, while destructive, might also seed the cosmos with the heavy elements necessary for planets and life to form. It's a reminder that even the universe's most violent events can play a role in its grand story. As we unravel the mystery of gamma-ray bursts, another cosmic enigma beckons, one that's equally dense and far more bizarre. Neutron stars, the remnants of supernova explosions, are so dense that a single teaspoon of their material would weigh billions of tons. How do these stellar corpses defy the laws of physics, and what secrets do they hold about the extremes of matter? The answers might just rewrite our understanding of the universe itself. Picture a star so dense that a single teaspoon of its material would weigh billions of tons, a scale so unimaginable it feels like something out of science fiction. Yet these objects exist, and they're called neutron stars. Born from the fiery deaths of massive stars, neutron stars are the universe's most extreme laboratories, where matter is pushed to its absolute limits. This is the 10th cosmic enigma we're exploring, the extreme physics of neutron stars. When a star many times more massive than our Sun exhausts its fuel, it doesn't go quietly. Its core collapses under its own gravity, triggering a supernova explosion so powerful it can outshine an entire galaxy. What's left behind is a neutron star, a city-sized object packing the mass of a star into a sphere just a dozen miles across. The forces at play are so intense that protons and electrons are crushed together, forming neutrons and creating a material denser than anything else in the universe. But the strangeness doesn't stop there. Inside a neutron star, matter behaves in ways that defy our everyday understanding of physics. The core is thought to be a soup of exotic particles, possibly including quarks, the fundamental building blocks of matter that are no longer confined within protons and neutrons. Some theories even suggest the existence of strange matter, a hypothetical state of matter so stable it could transform anything it touches. On the surface, neutron stars are equally bizarre. Their magnetic fields are trillions of times stronger than Earth's, capable of ripping atoms apart from thousands of miles away. And then there's the phenomenon of superfluidity and superconductivity, where the star's interior flows without friction and conducts electricity with zero resistance. It's like a cosmic superconductor operating on a scale that challenges our understanding of how matter behaves under extreme conditions. Take the pulsar J0348+0432 for example. This rapidly spinning neutron star is so dense that its gravity is twice as strong as previously thought possible. Orbiting a white dwarf, it emits beams of radiation like a cosmic lighthouse, allowing scientists to test Einstein's theory of general relativity in ways that were once unimaginable. Neutron stars also play a crucial role in shaping the universe. When two neutron stars collide, they produce gravitational waves ripples in space-time and forge heavy elements like gold and platinum. These cosmic collisions are like factories for the universe's most precious materials, scattering them across the cosmos and seeding future generations of stars and planets. Studying neutron stars is no easy task. Their extreme conditions can't be replicated on Earth, so scientists rely on observations of their light, gravitational waves, and even the timing of their pulses to piece together their secrets. Each discovery pushes the boundaries of what we know, challenging us to rethink the laws of physics. What do these stellar oddballs tell us about the universe? They remind us that the cosmos is far stranger and far more wondrous than we ever imagined. Neutron stars are a testament to the extremes of nature, where matter is pushed to its absolute limits and the rules of physics are rewritten. As we marvel at these cosmic enigmas, another mystery awaits, one that's equally elusive and far more energetic. Cosmic rays, high-energy particles from deep space, bombard Earth constantly, yet their origins remain shrouded in mystery. What powers these cosmic projectiles, and what can they teach us about the universe's most violent events? The answers might just reveal the hidden forces shaping the cosmos. Every second, invisible projectiles from deep space bombard Earth, carrying energies so immense they defy comprehension. These are ultra-high-energy cosmic rays, particles traveling at nearly the speed of light, with energies millions of times greater than anything produced in the most powerful particle accelerators on Earth. This is the 11th cosmic enigma we're exploring, the origin of ultra-high-energy cosmic rays. The story begins with the detection of these enigmatic particles, a feat that requires some of the most sophisticated instruments on the planet. Giant observatories like the Pierre Auger Observatory in Argentina and the Telescope Array in Utah are designed to catch these rare events. When a cosmic ray hits Earth's atmosphere, it triggers a cascade of secondary particles, creating a faint but detectable signal. These observatories act as cosmic detectives, piecing together clues about the ray's origins and energies. Take the Oh My God particle, for example. Detected in 1991, this cosmic ray carried an energy of 320 exa-electronvolts, so powerful it was moving at nearly the speed of light, just a fraction slower. To put that in perspective, if a baseball had the same energy per atom, it could be thrown at nearly the speed of light. The sheer scale of this energy is staggering, but what makes it even more baffling is that we still don't know where it came from. Theories about the origins of these ultra-high-energy cosmic rays are as varied as they are intriguing. Some point to supernova, the explosive deaths of massive stars, as potential sources. Others suggest active galactic nuclei, the incredibly luminous cores of galaxies powered by supermassive black holes, could be responsible. These cosmic behemoths are capable of accelerating particles to unimaginable speeds, flinging them across the universe like cosmic catapults. But tracing these particles back to their sources is no easy task. Cosmic rays are charged particles, meaning they're deflected by magnetic fields as they travel through space. It's like trying to follow the path of a pinball in a chaotic maze. Every twist and turn obscures their origin. This makes pinpointing their exact sources one of the greatest challenges in astrophysics. What do these cosmic rays tell us about the universe? For one, they offer a glimpse into the most extreme environments in the cosmos, where particles are accelerated to energies far beyond anything we can recreate on Earth. They also provide clues about the structure of magnetic fields in space and the processes that shape the universe on the largest scales. But perhaps the most profound question is this: what could these cosmic rays reveal about the fundamental laws of physics? Could they hint at new particles or forces we've yet to discover? Or do they point to phenomena so extreme they challenge our current understanding of the universe? As we grapple with these questions, another cosmic mystery looms, one that's pulling galaxies toward it with an irresistible force. The Great Attractor, a mysterious region of space with a gravitational pull so strong it's drawing entire galaxies, including our own Milky Way, toward it. What lies at the heart of this cosmic anomaly, and what secrets does it hold about the large-scale structure of the universe? The answers might just reshape our understanding of the cosmos. Deep in the vast expanse of the cosmos, there's a force so powerful it's pulling thousands of galaxies, including our own Milky Way, toward it at a staggering speed of over 600 kilometers per second. This is the Great Attractor, a mysterious gravitational anomaly that has puzzled astronomers for decades. Hidden behind the dense dust and stars of our galaxy's central plane, its true nature remains one of the most tantalizing enigmas in modern astrophysics. This is the 12th cosmic mystery we're exploring, the gravitational pull of the Great Attractor. Imagine the universe as a cosmic river with galaxies flowing toward a hidden destination. The Great Attractor is like a whirlpool in this river, exerting an irresistible pull on everything around it. But what exactly is causing this immense gravitational force? The answer lies shrouded in the obscurity of the Milky Way's central bulge, a region so thick with dust and gas that it blocks our view of what lies beyond. It's like trying to peer through a dense fog with only faint hints of what's on the other side. One leading theory suggests the Great Attractor could be a massive cluster of galaxies, a cosmic metropolis so densely packed that its combined gravity tugs on everything nearby. Another possibility is that it's not just ordinary matter at work, but a colossal concentration of dark matter, the invisible scaffolding of the universe, creating a gravitational well deep enough to draw in galaxies from millions of light years away. To understand the scale of this mystery, consider the Shapley supercluster, located even farther beyond the Great Attractor. This colossal structure, containing tens of thousands of galaxies, is the most massive known concentration of matter in the observable universe. Some scientists believe the Great Attractor might be part of a larger flow, with galaxies being pulled not just by it, but also by the even more distant Shapley supercluster. It's like a cosmic tug-of-war, with galaxies caught between two immense gravitational forces. But observing the Great Attractor directly is no easy task. The Milky Way's central bulge acts like a cosmic curtain, blocking our view in visible light. To peer through this veil, astronomers rely on other wavelengths, such as infrared and radio waves, which can penetrate the dust and reveal the hidden structures beyond. Instruments like the Hubble Space Telescope and the Atacama Large Millimeter Array have provided glimpses, but much of the Great Attractor's true nature remains a mystery. What could this cosmic enigma reveal about the universe? For one, it offers a unique window into the large-scale structure of the cosmos. The Great Attractor and the flows of galaxies around it are part of the cosmic web, the intricate network of matter that shapes the universe on the grandest scales. Understanding its role could shed light on how galaxies form, move, and evolve over billions of years. And as we ponder the mysteries of the Great Attractor, another cosmic puzzle emerges, one that challenges our understanding of the universe's expansion. The Hubble Tension, a discrepancy in measurements of how fast the universe is expanding, has left scientists scratching their heads. Could this tension hold the key to unlocking even deeper secrets about the cosmos? The answers might just reshape our understanding of space, time, and everything in between. At the heart of modern cosmology lies a puzzle so perplexing it has divided scientists for years. It's called the Hubble Tension, a disagreement over how fast the universe is expanding. This 13th cosmic enigma isn't just a technical debate, it's a challenge to our very understanding of the cosmos. The story begins with the Hubble constant, a number that represents the rate at which the universe is expanding. Measuring this constant seems straightforward, but here's the catch. Two of the most trusted methods give wildly different results. On one hand, the Planck satellite, which studied the cosmic microwave background, suggests a slower expansion rate. On the other hand, the Hubble Space Telescope, observing distant stars and supernova, points to a faster one. The difference might seem small, just a few kilometers per second per megaparsec, but in the precise world of cosmology, it's a glaring discrepancy. What could be causing this tension? One possibility is that there's something missing in our models of the universe. Perhaps dark energy, the mysterious force driving cosmic expansion, behaves differently than we thought. Or maybe there are unknown particles or forces at play, subtly altering the universe's growth. Some scientists even suggest that our understanding of gravity itself might need updating, a prospect that could rewrite the rules of physics. Others argue that the tension might stem from systematic errors in our measurements. After all, calculating the Hubble constant involves piecing together data from vastly different sources: ancient light from the cosmic microwave background, the brightness of distant supernova, and the pulsations of variable stars. Each method comes with its own uncertainties, and bridging the gap between them is no small feat. The implications of this tension are profound. If it's not resolved, it could shake the foundations of the standard model of cosmology, the framework that has guided our understanding of the universe for decades. It's like discovering that a cornerstone of a building doesn't quite fit. Everything else might need to be adjusted to make sense of it. So, what does this mean for the future of cosmology? Could the Hubble tension be a clue to new physics, hinting at forces or phenomena we've yet to discover? Or is it a reminder that even our most precise instruments and theories have limits, and that the universe still holds secrets we can't yet fathom? As we grapple with this cosmic conundrum, another mystery emerges, one that's equally puzzling and far more elusive. The missing baryons, the ordinary matter that makes up stars, planets, and even us, seem to be hiding in plain sight. Where are they, and what can their absence tell us about the structure of the universe? The answers might just reveal the hidden threads weaving the cosmic web together. When we think of the universe's matter, it's easy to imagine stars, planets, and galaxies, the stuff we can see. But here's the startling truth: about half of the ordinary matter, the baryons that make up everything from galaxies to your morning coffee, is missing. This is the 14th cosmic enigma, the missing baryons problem. Where could this invisible half of the universe's ordinary matter be hiding, and what does its absence tell us about the cosmos? The mystery begins with the mismatch between theory and observation. According to our best simulations of the universe's evolution, there should be far more baryons, protons, neutrons, and other particles than we've been able to detect. These simulations, based on the Big Bang and the formation of cosmic structures, predict a specific amount of ordinary matter. Yet, when astronomers tally up all the visible stars, gas, and dust, they come up short. The missing baryons aren't just a small oversight, they're a significant chunk of the universe's total matter. So, where are they? One leading theory points to the warm-hot intergalactic medium, or WIM. This sparse, diffuse gas, heated to temperatures of hundreds of thousands of degrees, fills the vast voids between galaxies. It's like a cosmic fog, so thin and spread out that it's nearly impossible to see with traditional telescopes. But this isn't just any fog. It's thought to contain a significant portion of the missing baryons, woven into the filaments of the cosmic web. Imagine the universe as a giant spider's web, with galaxies at the intersections and these faint threads of gas stretching between them. The WIM could be the hidden threads holding the cosmic web together. Detecting this elusive matter is no easy feat. The gas in the WIM is so hot it emits X-rays, but these signals are faint and easily drowned out by other sources. To find it, astronomers rely on a technique called absorption spectroscopy. When light from distant quasars passes through the WIM, certain wavelengths are absorbed, leaving behind a fingerprint. It's like shining a flashlight through a foggy forest. The light that reaches you reveals the shape and density of the fog. But even with this method, the WIM remains a challenge to study, requiring some of the most sensitive instruments ever built. The implications of solving this mystery are profound. The missing baryons aren't just a cosmic accounting error, they're a key piece of the puzzle in understanding how the universe is structured. If we can locate them, we'll gain new insights into the cosmic web, the network of matter that connects galaxies across billions of light years. It's a reminder that even the ordinary matter in the universe holds extraordinary secrets. As we ponder the whereabouts of these elusive baryons, another cosmic mystery emerges, one closer to home yet no less enigmatic. Rising above and below the plane of our Milky Way are the Fermi Bubbles, two colossal structures of high-energy radiation stretching tens of thousands of light-years into space. What created these immense bubbles, and what do they tell us about our galaxy's violent past? The answers might just shed light on the forces shaping not just our galaxy, but the universe itself. Rising above and below the heart of our Milky Way, two colossal structures stretch tens of thousands of light-years into space, glowing with high-energy gamma rays. These are the Fermi Bubbles, massive, symmetrical lobes of radiation that defy explanation and hint at a dramatic chapter in our galaxy's past. This is the 15th cosmic enigma, the origins of the Fermi Bubbles. What created these immense structures, and what secrets do they hold about the Milky Way's turbulent history? Discovered in 2010 by the Fermi Gamma Ray Space Telescope, these bubbles are a testament to the power and mystery of our galaxy's core. Each bubble extends roughly 25,000 light-years from the galactic plane, forming a colossal hourglass shape centered on the supermassive black hole, Sagittarius A. But how did they form? One leading theory suggests they are the remnants of a massive outburst from the black hole itself. Imagine a cosmic eruption where jets of energy and particles were blasted into space millions of years ago, carving out these enormous structures. Another possibility is that they were created by a burst of star formation, with supernova explosions flooding the region with energy and radiation. The sheer scale of the Fermi Bubbles is staggering. If we could see them with the naked eye, they would span a third of the night sky, dwarfing even the brightest constellations. Yet their faint gamma-ray glow makes them invisible to traditional telescopes, requiring instruments like Fermi to map their presence. These observations have revealed intricate substructures within the bubbles, including filaments and shock waves, suggesting a complex history of energy release and interaction with the surrounding gas. But why are these bubbles so important? For one, they offer a unique window into the Milky Way's past. The energy required to create such structures suggests that our galaxy's core was once far more active than it is today. Could this mean that Sagittarius A was once a quasar, a luminous beacon powered by a voracious black hole? Or perhaps the bubbles are evidence of a cataclysmic event, like the collision of a massive gas cloud with the galactic center? Each theory paints a different picture of our galaxy's evolution, raising questions about how galaxies grow and change over time. Studying the Fermi bubbles is no easy task. Their faint signals are easily overwhelmed by other sources of gamma rays, and their immense size makes it difficult to observe them in detail. Yet, scientists continue to piece together their story, using advanced simulations and observations to unravel the forces that shape them. Each discovery brings us closer to understanding the dynamic processes at work in our galaxy's heart. What could the Fermi bubbles reveal about the Milky Way's future? Could similar events occur again, reshaping the galaxy in ways we can't yet predict? These questions remind us that even our own cosmic backyard holds mysteries waiting to be uncovered. And as we explore these enigmatic structures, another cosmic puzzle awaits, one that lies at the very edge of our solar system. The Kuiper Cliff, a sudden drop-off in the number of objects beyond Neptune, challenges our understanding of how the solar system formed. What lies beyond this mysterious boundary, and what can it tell us about the origins of our cosmic neighborhood? The answers might just rewrite the story of our solar system's birth. Beyond the orbit of Neptune, in the cold, dark reaches of our solar system, lies a boundary that defies explanation. This is the Kuiper Cliff, a sudden, dramatic drop in the number of objects in the Kuiper belt, a region filled with icy bodies left over from the solar system's formation. It's as if someone drew a line in the cosmic sand and said, "This far and no farther." This abrupt edge is the 16th cosmic enigma we're exploring, and it challenges everything we thought we knew about how our solar system came to be. The Kuiper belt is often described as a cosmic junkyard, filled with remnants of the early solar system. These icy objects, including dwarf planets like Pluto, offer clues about the conditions that shaped our cosmic neighborhood billions of years ago. But when astronomers mapped the distribution of these objects, they noticed something strange. Beyond about 50 astronomical units from the Sun, 50 times the distance from Earth to the Sun, the number of objects drops off sharply. This sudden boundary, the Kuiper Cliff, doesn't fit with our models of how the solar system formed. If the Kuiper belt is a leftover from the primordial disk of material that birthed the planets, why does it end so abruptly? One compelling theory points to the gravitational influence of an undiscovered planet. Some scientists speculate that a massive object, often referred to as Planet 9, could be lurking in the outer solar system, its gravity sweeping the Kuiper belt clean of objects beyond a certain distance. This hypothetical planet, estimated to be several times the mass of Earth, could have shaped the Kuiper Cliff over billions of years, sculpting the edges of the solar system in ways we're only beginning to understand. While no direct evidence of Planet 9 has been found yet, its gravitational fingerprints are hard to ignore. Another possibility is that the Kuiper Cliff is a relic of the solar system's chaotic early history. During the formation of the giant planets, gravitational interactions could have flung many objects out of the Kuiper belt entirely, leaving behind a sharp boundary. Imagine a cosmic game of billiards with planets like Jupiter and Saturn acting as the cues, scattering smaller bodies across the solar system. This theory aligns with what we know about the dynamic processes that shaped the early solar system, but it doesn't fully explain why the drop-off is so sudden. The New Horizons mission, which flew past Pluto in 2015, has provided invaluable insights into the Kuiper belt and its mysteries. By studying objects like Arakoth, a pristine remnant from the solar system's infancy, scientists are piecing together the story of how these distant regions formed. Yet, even with these discoveries, the Kuiper Cliff remains a puzzle, a reminder that our solar system still holds secrets waiting to be uncovered. What does this enigmatic boundary mean for our understanding of the solar system's history? Could it point to a hidden planet, or is it evidence of processes we've yet to comprehend? The answers might not only reshape our view of the Kuiper belt, but also reveal new truths about how planetary systems form and evolve. As we ponder the mysteries of the Kuiper Cliff, another enigma beckons, one that comes not from the icy reaches of our solar system, but from the depths of space itself. The WOW signal, a brief but powerful radio burst detected in 1977, has captivated astronomers for decades. What could have produced such a strong, fleeting signal, and could it be a message from beyond our world? The answers might just challenge our place in the cosmos. On a quiet August night in 1977, a radio telescope in Ohio picked up something extraordinary, a signal so strong and unusual that it made astronomer Jerry Amon circle it on the printout and write, "Wow." In the margin, this single word gave the signal its name, and it has since become one of the most tantalizing mysteries in the search for extraterrestrial intelligence. The WOW signal lasted just 72 seconds, but its implications have echoed for decades. This is the 17th cosmic enigma we're exploring, the unexplained origin of the WOW signal and what it could mean for our understanding of life beyond Earth. The signal came from the direction of the constellation Sagittarius, and its intensity was unlike anything ever detected before. It matched the characteristics scientists had long predicted for a signal from an intelligent civilization. It was narrow in frequency, as if it had been deliberately transmitted, and it appeared to originate from deep space. Yet, despite numerous attempts to detect it again, the signal has never been repeated. It's as if the universe whispered a secret and then fell silent, leaving us to wonder what or who might have sent it. So, what could have caused the WOW signal? One possibility is that it was indeed a message from an extraterrestrial civilization, a fleeting attempt to reach out across the cosmos. Another theory suggests it could have been a natural phenomenon, like a comet or a burst of cosmic radiation, mimicking the characteristics of an artificial signal. Yet, no natural explanation has fully accounted for its unique properties, leaving the door open to the tantalizing idea that we might not be alone. The search for answers has been a cornerstone of the Search for Extraterrestrial Intelligence, or SETI, program. For decades, scientists have scanned the skies for signals like the WOW signal, hoping to catch another glimpse of something that could hint at life beyond our planet. Projects like the Allen Telescope Array and Breakthrough Listen have expanded this search, using advanced technology to sift through the cosmic noise for signs of intelligence. Yet, despite these efforts, no signal has matched the WOW signal's intensity or intrigue. What makes the WOW signal so compelling isn't just its mystery, it's what it represents. If it was indeed a message from another civilization, it would be one of the most profound discoveries in human history. It would mean that we're not alone in the universe, that somewhere out there, another intelligent species is reaching out across the void. Even if it turns out to be a natural phenomenon, it reminds us that the cosmos is full of surprises, waiting to challenge our understanding of reality. As we ponder the implications of the WOW signal, another cosmic mystery emerges, one that arrived in our solar system from the depths of interstellar space. In 2017, astronomers detected a strange, cigar-shaped object speeding through our solar system, the first confirmed visitor from another star system. Named Oumuamua, this enigmatic object defied explanation, sparking debates about its origins and nature. Was it a comet, an asteroid, or something even more extraordinary? The answers might just reshape our understanding of the universe and our place within it. In October 2017, astronomers made an extraordinary discovery, a strange, cigar-shaped object hurtling through our solar system at breakneck speed. Named Oumuamua, Hawaiian for scout or messenger from afar, it was the first confirmed visitor from another star system. This interstellar traveler was unlike anything we'd ever seen before, and its bizarre behavior has left scientists scratching their heads ever since. This is the 18th cosmic enigma, the mystery of Oumuamua and what it reveals about the universe beyond our solar system. When Oumuamua was first spotted by the Pan-STARRS telescope in Hawaii, it was already on its way out of the solar system, having passed close to the Sun. Its elongated shape, estimated to be up to 10 times longer than it was wide, was unlike any asteroid or comet we've observed. Most objects in our solar system are roughly spherical or irregular, but Oumuamua's needle-like form was something entirely new. Adding to the intrigue, it didn't behave like a typical comet. While most comets develop a glowing tail as they approach the Sun, Oumuamua showed no such signs despite its close encounter. But the real shock came when astronomers noticed something even more unusual. Oumuamua was accelerating, as if being pushed by an unseen force. This behavior defied the laws of gravity as we understand them. Comets can accelerate due to the outgassing of material as they heat up, but there was no visible evidence of such activity from Oumuamua. So, what was causing this mysterious acceleration? Theories about Oumuamua's nature have ranged from the mundane to the extraordinary. Some scientists suggest it could be a rare type of comet, one that releases gas in a way that doesn't produce a visible tail. Others propose it might be an asteroid, perhaps a fragment of a larger body shattered by a cosmic collision. But then there's the more speculative idea. Could Oumuamua be an artificial object, perhaps even an alien probe? While this theory captures the imagination, most experts lean toward natural explanations, though they admit Oumuamua's behavior is unlike anything we've encountered before. Studying Oumuamua has been a monumental challenge. By the time it was discovered, it was already speeding away, leaving astronomers with only a brief window to gather data. Telescopes around the world trained their sights on this fleeting visitor, but much about its composition, structure, and origin remains a mystery. It's like trying to solve a puzzle with only a few of the pieces, fascinating but frustratingly incomplete. What does Oumuamua tell us about other star systems? Its existence suggests that interstellar visitors might be more common than we once thought, and that the building blocks of planetary systems could be shared across the galaxy. Each object like Oumuamua carries with it a story, a snapshot of its home system, and a glimpse into the processes that shape the universe. Could there be more of these cosmic travelers out there waiting to be discovered? The answer might just change how we view our place in the cosmos. As we ponder the mysteries of Oumuamua, another enigma emerges, one closer to home but no less perplexing. The Pioneer Anomaly, a tiny but persistent deviation in the trajectories of the Pioneer spacecraft, has puzzled scientists for decades. What could be causing these robotic explorers to drift off course, and what does it reveal about the forces at work in our solar system? The answers might just challenge our understanding of gravity itself. As the Pioneer 10 and 11 spacecraft ventured beyond the edges of our solar system, they carried with them the hopes and dreams of humanity's first steps into interstellar space. But as they journeyed farther from Earth, something strange began to happen. Both spacecraft were slowing down not by much, but enough to defy the predictions of Newton's laws of motion and Einstein's theory of general relativity. This tiny but persistent deviation, known as the Pioneer Anomaly, became one of the most perplexing puzzles in modern space exploration. This is the 19th cosmic enigma, the unexplained deceleration of the Pioneer spacecraft and what it reveals about the hidden forces shaping our universe. The anomaly was first noticed in the 1980s when scientists tracking the spacecraft's trajectories noticed a slight but consistent deceleration. It was as if an invisible hand was gently tugging the probes back toward the Sun, slowing their escape into the cosmic void. At first, the effect was dismissed as a minor error, perhaps caused by onboard systems or external factors. But as the years passed and the anomaly persisted, it became clear that something far more mysterious was at play. What could be causing this unexplained drag on humanity's farthest-reaching explorers? One leading theory points to thermal radiation. The spacecraft's radioactive power sources, designed to keep them operating in the cold depths of space, emit heat. This heat could radiate unevenly, creating a tiny but measurable force that pushes against the spacecraft's direction of travel. Think of it like a car engine sputtering out a small puff of exhaust. It's not much, but over billions of miles it could add up to a noticeable effect. While this explanation fits some of the data, it doesn't fully account for the anomaly's magnitude, leaving room for other possibilities. Another intriguing idea is that the Pioneer Anomaly might hint at new physics forces or phenomena we've yet to discover. Could there be subtle deviations from Einstein's theory of gravity, especially at vast distances from the Sun? Or perhaps the anomaly is a clue to dark matter or dark energy, the invisible forces shaping the cosmos on the largest scales. These theories, while speculative, remind us that even the tiniest discrepancies can lead to groundbreaking discoveries. The implications of solving the Pioneer Anomaly go far beyond these two spacecraft. Missions like New Horizons, which flew past Pluto and into the Kuiper belt, rely on precise calculations of gravity and motion to navigate the solar system. If there's an unknown force at work, it could affect how we design and operate future missions, from robotic probes to crewed spacecraft. It's a reminder that even as we push the boundaries of exploration, the universe still has secrets to reveal. What does the Pioneer Anomaly mean for our understanding of the cosmos? Could it be a clue to a deeper theory of gravity, one that unites the forces of nature in ways we've yet to imagine? Or is it a reminder that even our most advanced technology is subject to the whims of an unpredictable universe? These questions linger as we continue to explore the solar system and beyond, searching for answers that might reshape our understanding of reality itself. As we ponder the mysteries of the Pioneer Anomaly, another cosmic puzzle emerges, one that challenges our understanding of the universe's very structure. The axis of evil, a peculiar alignment in the cosmic microwave background, has left scientists questioning whether the universe is truly uniform or if there's a hidden directionality woven into the fabric of space and time. What could this alignment mean, and what secrets does it hold about the origins of the cosmos? The answers might just shake the foundations of modern cosmology. When we look at the universe, we expect it to be uniform, no preferred direction, no special alignment, just a vast, isotropic expanse stretching in all directions. But what if that assumption is wrong? What if the universe has a hidden axis, a subtle but undeniable directionality woven into the very fabric of space and time? This is the 20th cosmic enigma, the axis of evil, a peculiar and unsettling alignment in the cosmic microwave background that challenges everything we thought we knew about the cosmos. The story begins with the cosmic microwave background, or CMB, the oldest light in the universe. This faint afterglow of the Big Bang is like a snapshot of the infant cosmos, revealing the seeds of galaxies and the large-scale structure we see today. Yet, when scientists analyzed the CMB's temperature fluctuations, tiny variations in the heat left over from the Big Bang, they noticed something odd. These fluctuations weren't entirely random. Instead, they appeared to align with the plane of our solar system, as if the universe itself had a preferred direction. This unexpected alignment, dubbed the axis of evil, defies the principle of isotropy, the idea that the universe looks the same in all directions. Why is this alignment so troubling? For one, it undermines a cornerstone of modern cosmology, the cosmological principle, which states that the universe is homogeneous and isotropic on large scales. If the axis of evil is real, it could mean that our place in the cosmos isn't as arbitrary as we thought. It's like discovering that the walls of your house are subtly tilted, hinting at a hidden foundation you never knew existed. So, what could be causing this strange alignment? One possibility is that it's an illusion, a result of observational bias or incomplete data. For instance, the Milky Way's dust and gas could be distorting our view of the CMB, creating the appearance of an axis where none exists. The Planck satellite, which mapped the CMB with unprecedented precision, has been instrumental in testing this idea. Yet, even after accounting for these factors, the alignment persists, leaving scientists to grapple with more radical explanations. Another theory suggests that the axis of evil could be a clue to new physics forces or phenomena that operate on scales we've yet to comprehend. Some scientists propose that it might be evidence of a multiverse, with our universe being just one bubble in a vast cosmic foam. Others speculate that it could hint at a fundamental anisotropy in the laws of physics, challenging the very foundations of our understanding. It's as if the universe is whispering a secret, and we're only just beginning to hear it. The implications of the axis of evil are profound. If it's real, it could reshape our understanding of the universe's structure and evolution. It might even force us to rethink the Big Bang itself, opening the door to new theories about how the cosmos began. For now, the axis of evil remains one of the most tantalizing and controversial mysteries in cosmology, a reminder that even our most cherished assumptions can be called into question. As we ponder the mysteries of the axis of evil, another cosmic enigma emerges, one that's equally vast and far more empty. The Boötes Void, a region of space so devoid of galaxies it's often called the Great Nothing, challenges our understanding of how matter is distributed in the universe. What could have created this immense cosmic desert, and what does it reveal about the universe's structure? The answers might just uncover the hidden forces shaping the cosmos. Imagine a region of space so vast and empty that it defies our understanding of the cosmos. This is the Boötes Void, a cosmic desert spanning over 300 million light-years, containing far fewer galaxies than anyone expected. If the Milky Way were placed at its center, the nearest galaxy would be millions of light-years away, a staggering expanse of nothingness. This 21st cosmic enigma isn't just a curiosity. It's a challenge to everything we thought we knew about the universe's large-scale structure. The Boötes Void, also known as the Great Nothing, was discovered in the 1980s during a survey of galaxy distributions. While most of the universe is organized into a vast cosmic web, filaments of galaxies connected by vast, empty voids, the Boötes Void stands out for its sheer scale and emptiness. Most voids are relatively small, but this one is colossal, stretching across a significant fraction of the observable universe. It's like finding a hole in a sponge that's larger than the sponge itself. How could such a massive region of space be so empty? One leading theory suggests that the Boötes Void might be the result of a collision between bubble universes. In the multiverse model, our universe is just one of countless bubbles floating in a higher dimensional space. If two of these bubbles collided, the impact could have pushed matter out of a region, leaving behind a vast void. It's like two soap bubbles merging, with the area where they touch becoming a gap in the foam. While this idea is speculative, it offers a tantalizing explanation for the void's existence. Another possibility is that the Boötes Void isn't as empty as it seems. Observational limitations might make it appear emptier than it actually is. Galaxies in the void could be faint or obscured by dust, making them harder to detect. The Sloan Digital Sky Survey, one of the most ambitious mapping projects in astronomy, has been instrumental in uncovering galaxies hidden within the void. Yet, even with these discoveries, the Boötes Void remains one of the most mysterious regions in the universe. What does the Boötes Void tell us about the cosmos? For one, it challenges our understanding of how matter is distributed on the largest scales. The cosmic web is thought to form through the gravitational pull of dark matter, with galaxies clustering along its filaments. But the Boötes Void's emptiness suggests that this process isn't uniform. There are pockets of space where the rules seem to break down. Could this void be a clue to new physics, or is it simply an extreme example of the universe's natural variability? As we ponder the mysteries of the Boötes Void, another cosmic puzzle emerges, one that stretches the boundaries of reality itself. The concept of the multiverse, a vast collection of universes beyond our own, has captured the imagination of scientists and dreamers alike. Could the Boötes Void be a window into this grander reality, a glimpse of what lies beyond the edges of our universe? The answer might just redefine our place in the cosmos. This brings us to the final enigma, a mystery that ties together all the others, the multiverse. If our universe is just one of countless others, each with its own laws of physics, what does that mean for our understanding of reality? Could the mysteries we've explored, dark matter, dark energy, black holes, and even the Boötes Void, be pieces of a much larger puzzle, one that spans not just our universe but an infinite tapestry of others? The journey to uncover these answers is just beginning, and the cosmos is waiting to reveal its deepest secrets. What if our universe is just one page in an infinite cosmic library, each book containing a universe with its own unique set of rules? This is the tantalizing idea at the heart of the multiverse theory, a concept that suggests our universe might be just one of countless others, each with its own physical laws, constants, and even dimensions. It's a theory that stretches the boundaries of imagination, challenging us to rethink everything we thought we knew about reality. This is the 22nd cosmic enigma, the multiverse theory's implications and what it means for our place in existence. The multiverse idea doesn't come out of nowhere. It's rooted in some of the most profound theories in modern physics. Take cosmic inflation, for example, the rapid expansion of the universe in its earliest moments. Some scientists suggest that this inflation didn't just happen once, but continues eternally, creating countless bubble universes like ours. Each bubble could have its own unique properties, governed by different physical laws. It's like bubbles forming in a pot of boiling water, each one a self-contained universe floating in a vast cosmic sea. Then there's string theory, a framework that attempts to unify all the forces of nature. String theory proposes that the fundamental building blocks of the universe aren't particles, but tiny, vibrating strings. To make the math work, string theory requires extra dimensions, 10 or more depending on the version. Some physicists suggest that these extra dimensions could house other universes, each one a separate brain in a higher dimensional space. Imagine our universe as a sheet of paper floating in a stack of other sheets, each one a parallel reality. But here's the catch: testing the multiverse hypothesis is incredibly difficult. By definition, these other universes would exist beyond the reach of our observable universe, making them nearly impossible to detect directly. So, how do we explore an idea that might forever lie beyond our grasp? One approach is to look for indirect evidence, like anomalies in the cosmic microwave background, the afterglow of the Big Bang, that could hint at collisions between our universe and another. Another possibility is to search for signatures of higher dimensions, such as unexplained gravitational effects or particles that behave in strange ways. What makes the multiverse so fascinating isn't just the science, it's the philosophical implications. If there are infinite universes, each with its own laws of physics, what does that mean for our understanding of reality? Could there be a universe where gravity works differently or where time flows backward? The quantum multiverse, a related idea, suggests that every possible outcome of a quantum event spawns a new universe. In this view, every choice you've ever made and every choice you didn't make exists somewhere in the multiverse. It's a dizzying thought, one that blurs the line between science and science fiction. Yet not everyone is convinced. Critics argue that the multiverse theory is untestable, making it more of a philosophical idea than a scientific one. Without a way to observe or measure these other universes, they say, the multiverse remains in the realm of speculation. But for its proponents, the multiverse is a natural extension of our best theories, a way to explain the fine-tuning of our universe's physical constants. If the multiverse exists, it could mean that our universe isn't special, it's just one of many, each one a roll of the cosmic dice. What does the multiverse mean for humanity's place in existence? It's a question that invites us to reflect on the scale of the cosmos and our role within it. If our universe is just one of countless others, does that make us insignificant, or does it highlight the wonder of our existence in a cosmos filled with infinite possibilities? The multiverse challenges us to think bigger, to imagine a reality far grander and more mysterious than we ever thought possible. As we wrap up this journey through the cosmos, we've explored 22 of the universe's most profound mysteries, from the invisible forces of dark matter and dark energy to the extreme physics of black holes and neutron stars. Each enigma has pushed the boundaries of our understanding, reminding us that the universe is full of surprises. And while we may not have all the answers, the questions themselves inspire us to keep exploring, to keep wondering, and to keep reaching for the stars. The cosmos is vast, but so is our curiosity, and that's what drives us forward, one mystery at a time. As we reach the end of this cosmic journey, it's worth taking a moment to reflect on the 22 mysteries we've explored, each one a testament to the boundless wonder of the universe. From the invisible grip of dark matter to the explosive brilliance of gamma-ray bursts, these enigmas remind us that the cosmos is far stranger, far more beautiful, and far more complex than we could ever imagine. They challenge our understanding, push the limits of human knowledge, and inspire us to keep asking the big questions. What is the universe made of? How did it begin? And what lies beyond the edges of what we can see? Think about it. Every discovery, every breakthrough starts with a question. The mysteries of dark energy and the Hubble tension aren't just scientific puzzles, they're invitations to explore, to wonder, and to dream. They remind us that the universe is a living, evolving story, one that we're only just beginning to read. And while we may not have all the answers yet, the journey of discovery is just as thrilling as the destination. These enigmas also remind us of our place in the cosmos, a tiny speck in a vast, interconnected web of galaxies, stars, and planets. Yet, even as we marvel at the scale of the universe, we're also reminded of the power of human curiosity. It's this curiosity that drives us to build telescopes that peer into the depths of space, to send probes to the farthest reaches of the solar system, and to dream of one day unraveling the universe's deepest secrets. So what's next? The mysteries we've explored today are just the beginning. Each one opens the door to new questions, new possibilities, and new adventures. Whether it's the hunt for missing baryons, the search for Planet 9, or the quest to understand the multiverse, the cosmos is full of surprises waiting to be uncovered. And you don't have to be a scientist to join the journey. Every time you look up at the night sky, every time you wonder what lies beyond, you're part of this grand exploration. As Carl Sagan once said, somewhere something incredible is waiting to be known. That's the beauty of the universe. It's always ready to surprise us, to challenge us, and to inspire us. So let's keep asking questions, keep exploring, and keep dreaming. The cosmos is vast, but so is our potential to understand it. If you've enjoyed this journey through the universe's greatest mysteries, don't stop here. Share your thoughts in the comments below. What mystery fascinates you the most? What cosmic question keeps you up at night? Don't forget to subscribe and join us as we continue to unravel the secrets of the cosmos. Together, we can explore the unknown, one mystery at a time. The universe is waiting. Let's see what we can discover.